So today we'll start looking at parametric functions. So with parametric functions, and hopefully you did some of this in pre-cal, yes? You have vague memories of it? Basically with a parametric function, I used to liken it to, and I find that students don't know what this is. Did either of you ever play with like an Etch-a-Sketch when you were a kid? Where each knob controls something different? Well, that's exactly what parametric equations are. The horizontal, the x, and the vertical, the y, are controlled separately, as opposed to, the vertical being controlled as the horizontal moves. And so usually the parameter is t, and the reason they use that is frequently it's time. Not always, but frequently it's when you do applications of this, you're doing it over time. So for example, if you graph x equals 3 cosine t, y equals 5 sine t, it traces an ellipse. Hopefully that sounds somewhat familiar to you. Well, now let's move on to the calculus part of it. So slope and concavity. So if x and y are both differentiable functions of t, and dx dt is not equal to 0, then dy dx is going to be equal to dy dt divided by dx dt. The change in y with respect to t divided by the change in x with respect to t. And that's going to be your slope. If you evaluate that at a particular point, then you have the slope at that particular point. Now, if y prime, which is dy dx, is also a differentiable function of t, then the second derivative of y with respect to x is a derivative with respect to x of y prime. So that is dy prime dt divided by dx dt. Occasionally students get really mixed up on that, and they believe that you need to take the derivative of y again, and you need to take the derivative of x again. But you don't need to take the derivative of x again. What you're going to do is you're going to take the derivative of y prime. So you've already put these together. Right, when you find this part, you've already done dy dt over dx dt. And so, students are like, well, wait a minute, isn't it supposed to be, the second order differential in x? Well, yeah, but you're doing that because you're taking the derivative of this thing when you do this. You're actually getting another derivative. Anyway, so let's take a look at this. For the parametric curve, x equals t squared minus 5 and y equals 2 sine of t, on the interval from 0 to pi, find the highest point on the curve and the coordinates of all points of inflection. So we're not just finding the first and second derivative, we're actually applying them on these problems. So to find the highest point on a curve, well, we want to find the maximum value of y. And on this particular one, we don't really have to do any work, since y is equal to 2 times sine of t, and sine of t's maximum value between 0 and pi is 1. That's going to be equal to 2. There's really not any work that you would have to show for a problem like that. Now, that is the maximum value. It did ask us find the highest point, so it's a little ambiguous in the way that it's worded. On the AP exam, they're a little more careful about how they word this. When they say point, to me that means find the coordinates. So we would need to know, well, when does that happen? And that's going to happen at pi. right? So the coordinates of that point are pi comma 2. Sorry, that's not correct. Duh. Maximum is at 2, but it is t that is pi, not x that is pi. So it's a real easy mistake to make. So it's going to be pi squared minus 5, 2. And that's one of the things you have to kind of guard against. You're so used to, you find this point and you're like, oh, the value that I used is the x value, it's actually the t value here. Okay, and then for points of inflection for this graph, we need to find places where the second derivative changes sign. So we're going to have to do a fair bit of work for this part. So dy dt is going to be 2 cosine of t, and dx dt is going to be 2t. So y prime is 2 cosine of t over 2t, or just cosine of t over t. So then dy prime with respect to t, sorry, just looking at something. We're going to have to use the quotient rule, which we haven't used in quite a long time, feels like at least. So that'll be t times the derivative of cosine, which is negative sine of t, minus cosine of t times the derivative of t, which is 1, all over t squared, which would simplify to negative t sine t minus cosine t over t squared. So the second derivative, d squared y dx squared, is dy prime dt, so negative t sine t minus cosine t all over t squared, over dx dt, which is 2t. So that's going to be negative t sine t minus cosine t over 2t cubed. And we want to know on the interval from 0 to pi, when does this change sign? So we need to find where that's equal to 0. And when a fraction is equal to 0, that means the numerator's got to be 0. So this means negative t sine t minus cosine t is equal to 0. And since that's got both a both trig functions and polynomial mixed together, that's always a chance for you to use your calculator to solve that. So I'll grab my calculator and go, okay, first of all, wake up. And then I'm sure I've been using this for geometry, so I need to change it back to radian mode. And clear that out. So negative x sine of x minus cosine of x on a window from 0 to pi. And we know that the maximum value on this is going to be 2, right? So I'll assume that the minimum is negative 2, so I'll go from negative 3 to 3. That was for the original. Don't know what the second derivative is going to be, but I only need to know where this is equal to 0, so let's see what happens. For a moment there, you were worried that there weren't going to be any. I certainly was. So we find the 0 of that. I'll make my right bound pi. Oops. Ooh, what do I want to guess? I'm going to guess 2.89. Well, that's not bad. 2.783. Notice that if you had to justify your answer, be sure that you don't say, because this is where the second derivative is 0. It's where the second derivative changes from negative to positive in this case, or positive to negative. All right. So we did arc length earlier in the year. We can also find the arc length of a parametric curve. So if a parametric curve is traced once as t increases from t sub 1 to t sub 2, and dx dt and dy dt are both continuous functions of t, then the length is the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared. Now you may remember that when we did arc length earlier, it was 1 plus dy dx squared underneath the square root, right? Here we have both because it's changing both in the x direction and in the y direction at the same time. Or at least that's the way I think about it. That, and this is dt. On the other one it was dx. So anyway, so this says find the length of the asteroid, not asteroid, but asteroid, different word, x equals cosine cubed t, y equals sine cubed t on the interval from 0 to 2 pi. So I need to find the derivative of both of those with respect to t. So dx dt is 3 cosine squared of t times negative sine of t, because of the chain rule, and dy dt is going to be 3 sine squared of t times cosine of t. So the length of the curve should be the integral from 0 to 2 pi. And if you were doing this, you would want to check to make sure that from 0 to 2 pi it just did the curve once. It didn't start going back over itself. This would be the square root of 3 cosine squared t sine t, and you may object that I dropped the negative sign, but I'm squaring it, so it doesn't matter. You can put it in if you like. Plus 3 sine squared t cosine t quantity squared dt. So math 9, the integral from 0 to 2 pi of the square root of, I need a set of parentheses there, 3. I usually, when it's cosine squared or sine squared, I usually just type it cosine of x, cosine of x. Otherwise, you have so many parentheses that I start to get lost in it. I mean, just for me, that's better. And then times sine of x. Now I need to close that parentheses and square it. Plus, open a new set of parentheses, 3 sine of x, sine of x, cosine of x, and square that, all with respect to x. La 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 la. And it turns out after all of that, the length is 6. It's always surprising when something like that happens. You're like, what? So, last example, the path traced by a point on a wheel's edge as the wheel rolls is called a cycloid. Find the length of one arch of the cycloid x equals a times t minus sine t, y equals a times 1 minus cosine t on the interval from 0 to 2 pi. So what's going on there is, let's actually graph this. Obviously we can't put the a in because that's some constant, but we can put everything else in and kind of see, well, what does this thing look like? If we're going to do that, then we need to change our mode to parametric mode. And then we're going to have t minus sine t. And notice that when you change to parametric mode, it automatically changes the variable to t. And 1 minus cosine of t on the interval from 0 to 2 pi, which is, it's already set there. So I'm just going to leave it and say, graph that. Let's make it a little longer so we can see a little more of it. Let's go to, say, 8 pi. Oops, not e, pi. Okay, still not e. There we go. Something's not right. Did you notice it graphed exactly the same thing? t minus sine of t and 1 minus cosine of t. I don't know what I did wrong. Because the y value should be 0 when cosine is 1. So when you get to 2 pi, where cosine is 1, it should go back to 0 again. Weird. Okay. So it did it there. Oh, I didn't make the x big enough, probably. Okay, that's what happened. I didn't make the x window big enough. Yeah, that's what happened. Okay, I was like, man, something's badly wrong. So what's happening is it makes this graph that looks like this. So if you can imagine, if you were to take a wheel and stick something on it and trace that path as the wheel rolled along the ground, that shape is what it makes. It's called a cycloid. Anyway, so we need dx dt, which is going to be a times 1 minus cosine t, and dy dt, which is a times sine of t. So then the length is going to be equal to the integral from 0 to 2 pi of the square root of, this will be a times 1 minus cosine of t squared plus a times sine of t squared dt. Now, in order to make that a lot easier to do on your calculator, notice that we're going to have an a squared as a factor of the first term and an a squared as a factor of the second term. So we can factor that out and make this a times the integral from 0 to 2 pi of the square root of 1 minus cosine of t squared plus sine of t squared dt. So I have the integral from 0 to 2 pi of the square root of 1 minus cosine of t. Notice you have to put in two parentheses there, one for closing the cosine and one for closing the 1 minus. Squared plus, this is just sine t times sine t. So this comes out to be 8t. Okay, any questions about that?
What is A in that one?
Pardon?
What is A?
It's just a parameter.
Oh, okay.
It's just some constant. All right.